Oh, okay.
I'm just recording again.
Yeah, okay, no, I understand. So Claudio mentioned that I've worked in mixing for a long time. I actually started working in 1984 as an applications engineer for CheMe, who are also a mixing company. Did grad school and then ended up in the United States working for DuPont. But we're going to focus today on mixing and mass transfer in 2- and 3-phase systems. And as we go along, I'll stop and ask if anyone has any questions at certain points along the way. Okay, so here's what I want to talk about: characterization of impellers. There's a number of different shapes of impellers that we and our competitors would try to sell to you. So how do we quantify their mixing performance? That's what we'll talk about first. Then we're going to talk about process results. And the first is solid liquid mixing in fast settling systems. I know there's a lot of interest about high solids, viscous non-Newtonian slurries, but we don't really have time to get into that today and cover all this material. And I'm more than happy if Claudio and some people at the university can set up another opportunity to talk about viscous mixing, but it's a separate subject. Then we'll talk about gas liquid mixing. I say a few words about 3-phase mixing, where we've got solid, liquid, and gas, and then finally some conclusions. So what is a mixer? So a mixer is a pump, and most engineers, chemical engineers and mechanical engineers, are taught about pumps, and we look at a machine that generates flow, and it supplies energy, it supplies power to the fluid. So for an agitator in a stirred tank, the flow and the power can be calculated from using 2-dimensionless numbers. The first is the flow number. And I've just realized I haven't got a nomenclature. I'll send a nomenclature to which hopefully Claudio can then distribute to everyone attending. First is the flow number, which is the flow generated by the impeller divided by the speed and the diameter of the impeller. And the second is the power number, which is the power divided by the density of the fluid, the speed cubed, and the diameter of the impeller raised to the power 5. So those quantities have to be measured. And then there are other quantities which are dependent on the impeller geometry. The first of which is the impeller to tank diameter ratio. And the second is the ratio of the diameter of the impeller to its projected height at its tip. And we'll say we're going to talk about why these numbers are important as we move along. So these are the impeller types that we sell and our competitors sell for low viscosity, medium viscosity mixing. So the top line of impellers are called hydrofoils, and they're profiled. They're shaped like an aeroplane wing or a boat propeller. Then we have the flat, essentially turbines. We take a plate and we attach it to the shaft, either angled at 45 degrees or 90 degrees, and they're said to be mixed flow. And finally, we have the disk turbines, which are most commonly used for gas dispersion. So the way these agitators or impellers are described in the industry is that the hydrofoils are low shear and high efficiency, and the disk turbines are high shear and low efficiency. So I mentioned the ratio, this dimension of the projected height of the impeller. This is the ratio that we're looking at, and it's different for different impellers. The projected height of the hydrofoils is smaller for a given diameter than a pitch blade turbine or a flat blade turbine. So if you look in the literature, it's generally accepted that hydrofoils are low shear, high efficiency, and disk turbines are high shear and low efficiency in terms of their pumping capabilities. So we can calculate the flow that the impeller generates if we know its flow number. but all that tells us is the magnitude of the flow. It doesn't tell us where the flow is being directed. So one thing that we can actually do, these are the time averaged velocity profiles for 3 pitch blade turbines, which are measured using laser Doppler anemometry. And by changing the diameter of the impeller, we can change the direction of the primary flow off the blade. So if you look at these 3 impellers, and we're going to talk about this a bit later, which of those impellers is going to be most efficient for suspending solids? And we will answer that question a bit later. Why is the flow deflected with a large diameter pitch blade turbine? Well, there's a high pressure region developed underneath the blade, which deflects the flow out towards the wall of the tank. So we can measure the flow. We can direct the flow where we want to go depending on the diameter of the blades and also the angle of the blade. So if I have a 90-degree vertical blade, the flow is going to be directed radially out towards the wall of the tank. So now we can define the efficiency, and there's I actually have an article that was published in 2017, which I will also send to Claudio to distribute to everyone who's attending. So this chart, the details of how we developed that chart is covered in the article. But what we're plotting here is the hydraulic efficiency of these impellers, exactly as we define the efficiency for a centrifugal pump. It's the kinetic energy of the fluid moving, the flow, divided by the mechanical energy input by the machine. So what we have, the orange circles are narrow blade hydrofoils from different vendors. The green circles are pitch blade turbines. The yellow circle is a flat blade turbine. The light blue circles are Rushton turbines with the disc. And this green circle down here is a high shear disperser sawtooth blade, which we use to disperse, to disrupt, to generate high stresses to break up a second phase. We don't want it to be a pump. We want it to be a machine that will break up a second phase suspended in our slurry. So if we look at the diamonds are the values using which were measured in our lab for various hydrofoils and the pitch blade turbine. So the message here is there's no magic. All the hydrofoils essentially have the same efficiency. All the pitch blade turbines have essentially the same efficiency. What we have to do is to understand our process and determine how do we want the energy to be used in the tank to best achieve our process result. What are we trying to do? Now, if we look at the hydrofoils, there's a range to say of between about 34% and 56%. And this is a result of the fact that we're not taking into account the impeller diameter here. We're only looking at the ratio of the power number and the flow number. So what happens if we take the impeller diameter into account? Now everything lines up. This is now an efficiency defined as kilograms of fluid moved per joule of energy input by the mixer. And now we have this quite helpful line, this slope. And what it tells us is that the most efficient impellers as pumps are the low viscosity, the larger diameter, this is the impeller to tank diameter ratio, hydrofoils. So as the power number increases, these are the pitch blade turbines, here's the flat blade, here's the Rushton turbine, the efficiency goes down. So if we're looking at a process which is driven by flow, where shear is not an important mixing characteristic that we need, we're going to choose a hydrofoil impeller of larger diameter, half the impeller half the tank diameter. But what we have to remember is that these impellers are actually going to be running at a high speed and a high tip speed. So if we have solids, which we think might be abrasive and erode the blades, we might actually have to use a less efficient impeller in order to reduce the tip speed of the impeller. So let me stop there. Let me stop and ask if anyone has any questions. Okay, so I'm going to keep moving. So the other side of the design equation that we need to look at is shear. So there's a book that was published by a guy called Jim Oldshue, Fluid Mixing Technology, published in about the early 80s. And he says, so he worked for Lightning, and we've been acquired by SPX Flow. We're now a sister company of Lightning. So what Jim Oldshue said was that, so in the A3 impellers are hydrofoils. So if you're familiar with Lightning, they have the A310, the A320s. These are hydrofoils with profiled blades. And the A2 series, the A200s, are pitch blade turbines. So what Jim Oldshue said was that a hydrofoil is lower shear because it has a flatter velocity profile than a pitch blade turbine. And a Rushton turbine has higher shear than a pitch blade turbine because it has an even steeper velocity profile. So if we test that theory, and say, well, if we look at data, we're looking at dispersing an oil. This is silicone oil dispersed in water, low concentration, so that the drop size is controlled by the breakup mechanism. We're neglecting coalescence. So if the model that Jim Oldshue suggested is true, well, the drops made with the Rushton turbine at the same power input should be smaller than the ones made by the pitch blade turbines, which should be smaller than the ones made by the hydrofoils. And down here are the drops made with the sawtooth blade. So there's something missing. And I'm not criticizing the work, the way Jim Oldshue approached this. I mean, he was doing this work nearly 40 years ago, and the tools that we now have to examine stirred tanks have many generations better than the ones that he had available. But this is just drop size plotted versus power per unit mass. So what's missing? Oops. Okay, come on, start. So this is a Rushton turbine blade moving through, and this is data. This isn't a model. We're using a device called a particle image velocimeter to look at the flow coming off the tip of the blade. And what you can see is there's a vortex forming. There's a vortex forming at the tip of the blade where the high shear region on the front of the blade meets the low pressure region on the back of the blade. This vortex forms. And this is the hot spot. This is the region in the tank where the local energy dissipation rate, the local power per mass is a maximum. And this is the region where the drops are created. Once they're created, they move away. And as they come back, they may be broken up again. And eventually we get to an equilibrium drop size where the forces, the stresses pulling the drops apart are balanced by the resistance due to the viscosity of the drop and the interfacial tension. So this is a CFD model. This is using a technique called large eddy simulation to model the trailing vortex coming off the blades. And we see there's one above and one below. For a Rushton turbine, for other impellers, there's only one. And the size of the vortex is a function, is proportional to the projected height of the blade at its tip, which is why that dimension is so important in understanding how to quantify impeller performance. So this is the same set of data measured that we showed before, now plotted versus the maximum energy dissipation rate in the trailing vortex. And again, I'm going to send the article that describes how this calculation is done to Claudio to circulate to everybody. The other interesting thing here is that the theory says that the exponent on power per unit mass should be -2/5, and it is. And the goodness of fit, I mean, the relative standard deviation on this is plus or minus 10%, which is really good for a mixing experiment. So an impeller in a stirred tank is a pump, and we can measure the power, we can measure the flow, we can measure the shear, the efficiency, and we can quantify these properties of the impeller quite accurately. So conventional wisdom is wrong. High shear impellers have a high energy dissipation rate in the trailing vortex, which relates back to the tip speed. It's a small diameter, small power number, small projected height. Low shear impellers have a low energy dissipation in the trailing vortex, so they have a large diameter, a large projected height, and a low tip speed. So think about the kind of impellers that you use for flocculation. Once you've added your flocculant, what kind of impellers do you use to promote the collision of the particles and the flocculation? And it's not a small diameter, high speed impeller. It's a large diameter, low speed impeller. And so we need to have a conversation, what's the process result, and choose the impeller to best optimize the balance of shear and flow to achieve that mixing result that we need for our process to work. So again, let me stop there and ask if anyone has any questions before we move on.
Sorry, Felipe Contreras from here. Related with the conventional theory, related with, for example, the power number, that you have a relation with the speed and diameter of the how do you say, the
impeller? Yes.
The impeller, yeah, thanks. This conclusion is in agreement with that, or how we can interpret this typical knowledge that is transferred in the universities from the conventional point of view is in agreement with this kind of conclusion?
Well, there aren't many universities that actually teach mixing. I mean, my position, this conclusion about the flow and the shear, the measurement of power, the measurement of flow, I'm very confident that that position is correct. And if you or anyone, whether working in a university or working in industry, wants education, more education about mixing, I would be more than happy to set up a seminar like this and cover the topics that you want to cover. And I will say, I mean, I realize that I've put a lot of information into like the first 20 minutes. We could talk for an hour just talking about characterization of impellers. So what I wanted to do is to set up the basics about the impeller selection, and then apply that understanding to solid liquid mixing, gas liquid mixing.
Yeah, that was my comment. In another way, yes, in our university, we don't enter in detail related with the mixing details, but always say, in order to scale up, for example, your experience in laboratory, in order to evaluate mass transfer or something like that, you can use maintain the Reynolds in order to keep the same pumping capacity. Use Reynolds in order to power power number.
Yes.
But the comment here is that you say that it's necessary to include a more detailed training courses or something like that in the universities?
I feel very strongly that we need more teaching about mixing. I mean, I'll give you, so if we say we scale up on constant Reynolds number, the power input per unit mass by the mixer will go down. I guess, and then we'll talk about this. I guess the point is you need to understand what about the mixing drives your process. What's the rate limiting step? And you need to scale up to keep the rate limiting step the same from the lab to the pilot to the full scale. And if you can do that, then your process will have the same time scales at the full scale. But the important thing to bear in mind is the rate limiting step may change as you scale up. Generally, if you scale up, Reynolds number increases. You may move from the transitional to the turbulent regime, and mixing will happen at a faster rate. So it's more complicated than just picking a number to keep constant as you scale up. It depends. I mean, it's dependent on what are you trying to what's your process result? What are you trying to achieve in your process? We can talk some more. We can talk some more. I mean, I'm happy to hang on the phone as long as people want to talk to me this afternoon. This will be very interesting.
Perfect. Thank you.
Okay.
Thank you very much.
So let me move on. So solid liquid mixing.
Can I ask you something quick?
Yeah, sure.
If I'm interested actually in dispersing air, you know, the plot you show about the variation of the bubble size or actually drop size in water, can I use the same approach and the same equations and the same analysis that you presented to us for air?
In a basic sense, you can, but there'll be other things affecting the bubble size. And actually, bubble size is very. I'm going to talk about this after we've done solid liquid. It's very difficult to measure bubble size, but you can infer the bubble size from the interfacial area of the bubbles, which you can back out from the KLA, the volumetric mass transfer coefficient. So I'm going to talk about that later. It's actually very difficult to measure bubble size in a stirred tank, but you can infer what the bubble size is from the mass transfer coefficient.
Okay, that's fine. Thank you.
Yeah, so we'll talk about that a bit
Sorry,
later. Okay.
sorry, Richard. Just an interesting comment. Just the person who's asking is Patricio Gomez, is one of the key inventors in the bubble size device. So you're talking with the guy who invented the sensor to measure bubble size distribution.
Oh, excellent. Okay, great.
So we'll have a conversation with him later.
Yeah, absolutely. Absolutely. That would be great. Thank you. Okay, so solid liquid mixing. So solids are suspended in a continuous liquid. So by suspending the solids, we're generating area for mass transfer between the phases. And we're suspending the part. So that's generally what we're trying to do. Or we're suspending the particles to create a slurry for transport. So we've got an iron ore or some ore, we slurry it up and then we pump it down a pipeline, the slurry to the plant where the ore is processed. It could be a chemical reaction. And we need to consider the balance of the mass transfer and the rate of reaction. And we may be mass transfer limited. And if we're mass transfer limited, can the rate of mass transfer be increased through mixing? And so that the mass transfer can keep up with the rate at which the various molecules are being consumed. Solid particles are dispersed in a continuous liquid, and sometimes the degree of uniformity of the slurry is required as a process result. So if we say we're having solids leaving the tank by overflow, then they must be suspended to the liquid surface. If they're leaving the tank from an outlet in the bottom of the tank, they don't necessarily have to be suspended so high. And then the other question is, how do we define uniformity? Is it uniformity by concentration, or is it uniformity by particle size? So if I have a wide range of particle sizes and say my largest particle is 1 millimeter, and I want that particle to leave the tank by overflow, that 1 millimeter particle has to be suspended to the liquid surface, or the larger particles are going to accumulate over time and eventually fill my tank. So I realize you guys are in Chile and I'm in the US. It's broad daylight out here, and a fox has just run down the street in front of my back garden. Amazing. Anyway, enough wildlife. So we put particles in and we suspend them. We may be forming particles through crystallization, through precipitation. Classic example in Chile right now is the precipitation of lithium carbonate from brine and sodium carbonate, or flocculation, where we have a suspension of very fine particles which we want to grow. We add a chemical to break down the van der Waals resistances, or and allow the particles to collide and stick together. And the process could be batch or continuous. So one of the things that's most important, even before you start designing your agitator, is to get good basic data. So this is a chart. The most recent paper that this chart appeared in is in Powder Technology, a paper written by Tim Bell back in 2005, a former colleague of mine at DuPont, we're looking at the successful startup of plants 1 year after startup. So we're looking at the percentage of the design rate. So if the feeds are liquids and gases, we're at 90%, the median is 90% of design rate. And within 1 year, some plants have actually exceeded their design rate. If we have a refined solid feed, so we're buying a crystal from another company, we're buying titanium dioxide from Chemours or an ingredient from BASF or Bayer, and we're putting that into our process so we know exactly the particle size and the density that we're getting. The median is 50% and the best is 90%. And if we have a raw solid feed, which is an ore, we're digging something out the ground and we have very little control over it, the median is 38% of nameplate. The best is about 80%, but in both the cases where there's solids, some of them haven't actually started up yet. So getting good basic data and understanding how to use it is really, really important in solid liquid processes. How do we define the degree of suspension? So this is a chart taken from one of our design books. So the minimum speed is called just suspended. Just suspended, some particles may be stagnant for a few seconds on the vessel base. Then we have off bottom, 50% uniformity, 90% uniformity, then uniform. And in uniform, it could be concentration or particle size. The particle size distribution is the same at all parts of the vessel. So this definition of particles being stagnant for a few seconds or more was first proposed by a guy called Leaching back in the late 50s, looking at published in Chemical Engineering Science, and is one of the classic papers on solid suspension. And we'll refer back to this this idea of a few seconds as we move along. So the question we're going to ask our customers, when you look at the degree of suspension and distribution, why do you need the particles suspended to the top of to the liquid surface? And the reason for that is the amount of energy that I need to put in to get from off bottom to uniform is a factor of 10, more or less, order of magnitude. So if you really need uniformity, you can have it, but it's going to cost you money to get there, both in terms of power and the size of the equipment that you're going to need to do this. So I like to take a step back and think about the physics, the mechanism by which my mixing process is happening. So kinetic energy is being supplied to the particles from the mean flow, the pumping, and the turbulence, which is being generated within the flow. So the particle gains potential energy as it's lifted up off the base of the vessel, and kinetic energy as it's moved. And this is essentially the same mechanism that you would see if you were designing a slurry pipeline. The force or energy balance between the particle and the liquid. So this is our starting point. So back in the late 70s and mid 80s, an Italian professor called Baldi and an English professor called Davis actually wrote down the force balance, an energy balance and a force balance. And in 2015, well, I started this work probably in around 2000, thinking about this. And so I and my co-authors, we took the Baldi Davis approach and applied it to a really, really large data set. 3 vessel scales, viscosities up to 2000 centipoise, water-like 2000 centipoise for hydrofoils and pitch blade turbines. And the following year, we then applied this same model to radial flow impellers, the Rushton turbines. So what the model predicts is that there are 2 regimes. So first, let me say that the way we take the physics, we take the model, we write the balances, and then we can express the equations dimensionlessly as a Reynolds number and an Archimedes number. So the Reynolds number that we're using is the Reynolds number of the turbulent eddies at the scale of the particles. Where our approach is to say it's those eddies, those turbulent eddies at that scale that are providing the energy to lift the particles up. And the Archimedes number is simply a dimensionless group that takes account of the density difference between the particle and the liquid viscosity, and the particle size. So the model that we developed says that for large Archimedes numbers, the gradient should be 1/2. And for smaller Archimedes numbers, the gradient should be 1/3. So this is for one set of data, one particle size and one concentration. It's sand in water. And what we see is when we do the regression on the data in the different regions, we do indeed get a gradient of 1/2 for high Archimedes number and a gradient of 1/3 for low Archimedes number. So this isn't just simply a regression fit. We're starting from the physics. And so it gives us a lot of confidence to use this approach for scale up.
Sorry, is the Reynolds number of the particles or the fluids?
It's the Reynolds number of the fluid.
Okay.
It's I actually have a backup chart that shows how we derive this Reynolds number, which we can have a look at the end. But it's essentially the Reynolds number of the turbulent eddy, which has a length scale equal to the size of the particle. It's not the Reynolds number of the particle settling. It is a property of the fluid, not the particle.
Okay, thanks.
Okay. So if we take the correlation and we rewrite them, we've got the just suspended speed, power number of the impeller, which we mentioned, diameter of the impeller, size of the particle, density difference. We've got now we're looking at the volume fraction of the solids, not the weight fraction of the solids, and a weak dependency of the C is the distance of the impeller above the base of the vessel. And for Rushton turbines, the geometrical dependency is different. Now it's the tank to vessel diameter, and there's a good exact reason for this, which I'm not going to dwell on right now. But if we look at this regression analysis, only 3 of the constants come out of the correlation, out of the regression. 4 of the constants are predicted by the physics. Okay, so I've just realized I haven't got the values of Z here. I will make sure that I pass those on to you also. So we've got the physics down. We've got a nice correlation, but in the world of research in academia, we use very tightly sieved particles. The particle size distribution is very narrow. But in the real world, the particle size distribution can be wide. So this is an example of a particle size distribution. Our maximum particle size is around 120 microns. We've got, it's slightly bimodal. The median particle size is about, let's say, 5 or 6 microns. So when we get inquiries from customers, they will tell us that they're interested in, that they want to suspend the D80. So what that means is that we're going to leave the large particles behind if we design on that basis. So yes, we can do that, but what's the consequence? So in this particular example, if we design for 120 microns, the speed at which we need to operate is 26% higher. The just suspended speed is proportional to the diameter of the particle raised to the 1/6 power. And it doubles the power. It doubles the power on the agitator. So the question is, it becomes an economic question. If I'm going to leave these big particles behind, how often am I going to have to go in and clear out the tank? And what does that cost me? Firstly, to do the clean out, and secondly, to shut the plant down for long enough to do that clean out. Is it actually worth spending the money to be able to suspend the largest particles in the distribution? It's an economic question. So if we design for less than the maximum particle size, particles accumulate small, there'll be a small number and volume, but how often will the vessel need to be cleaned? We should be able to estimate that. So what we have found, and other people who've done this work looking at these correlations, if you have a distribution and you know what that distribution looks like, the best way to account for the shape of the distribution is to use a quantity called the D43, which is the sum of the particle diameters raised to the power 4 divided by the sum of the particle sizes raised to the power 3, the cubed. And so it's weighted towards the high end of the distribution, but that seems to work when there is a distribution in particle sizes. So if we look at we can rearrange the correlation, and all I've done here is simply taken the power number, speed, and diameter onto this side. So these are all properties of the impeller. All the properties over here are properties of the system: the particle size, the concentration, and the density difference. And there's actually a G, an acceleration due to gravity missing there, which I apologize, I've just noticed. So if I multiply both sides by the impeller to tank diameter ratio, what I end up with over here is the power per unit mass input by the impeller raised to the 1/3. So what this tells us, because of the Z value, which I apologize again, is not included, and I will make sure it is included, at equal diameter, a pitch blade turbine requires twice the power of a hydrofoil. And a large pitch blade turbine requires 3.5 times the power of a pitch blade turbine, which is 1/3 the tank diameter, 1/2 to 1/3. So why is this? If we look back at the velocity profiles, the smaller impellers are directing the flow directly at the base of the tank where the particles want to sit. The large diameter pitch blade turbine is directing the flow out towards the corner. And the way that the particles are picked up is by being sucked up into this recirculation loop, which is much less efficient than directing the flow down to where the particles are sitting. So the laser Doppler anemometry and the velocity profiles are showing why the correlation works the way it does. So the next thing we want to look at is mass transfer. That's what we're trying to achieve between the particles and the liquid. So operation at the just suspended speed is the optimum for mixing and solid liquid mass transfer, if we're looking at solid liquid mass transfer. So all the particles are in motion and in contact with the liquid phase. And so Zwittering's definition is that the particles are not stationary for longer than 1 to 2 seconds. So the question is that overly conservative? What if they were stationary for 5 seconds or 10 seconds? And that's this is something that we're actively looking at right now. But we've shown that if we look at the difference between the smallest hydrofoil and the largest pitch blade turbine, the difference in power input can be a factor of 10. So what is the effect on the mass transfer coefficient and the rate of mass transfer? So the correlation that is commonly used to estimate the mass transfer coefficient is the Sherwood number correlation, which has the mass transfer coefficient KL, particle size, and diffusivity, and it's 2 plus. So if that particle is stationary in the liquid, the Sherwood number is 2. So as the fluid starts to move and we start to develop some Reynolds number, we get this additional term, the Sherwood number increases. So what we're going to do, traditionally people use the impeller Reynolds number. But where is the process occurring? It's occurring at the particle. So what we are going to do is to use that eddy Reynolds number, which is the Reynolds number of the flow at the scale of the particle, which is based on the power input per unit mass. And this is described in a book that John Davies wrote called Turbulence Phenomena, published quite a while ago. It is still available, but it says that the mass transfer coefficient is weakly dependent on the power input per unit mass, power per unit mass raised to the 1/4, provided that all the particles are in motion and being brought into contact with the fluid. So here's a quick example. Tank diameter, liquid depth is 3 meters. I've got a pitch blade turbine, density of 5,000 kilograms per cubic meter, liquid density of 1,000, particle size 500 microns, 25% weight, 6% by volume, diffusivity of 10 to the minus 9 meters squared per second. So here's the calculations. Just suspended speed is 170 RPM. I need a 50 kilowatt motor to drive the agitator, and my power per unit mass is 1.8 watts per kilogram. The interfacial area is 750 meters squared per meter cubed. KL is 6.25 times 10 to the minus 5 meters per second. And KLA is 4.69 times 10 to the minus 2. And the time scale of mass transfer to reach 99% of the equilibrium value is 5 over the KLA. And 5 over KLA is 110 seconds. So if the time scale of mass transfer is 110 seconds, do I really need my particles sitting on the base of the vessel for 2 seconds, for less than 2 seconds? And I think the answer is no. We may be able to design agitators with a lower power input if we understand how long the particles can be stationary before affecting the mass transfer rate. So this is a chart which I've copied from Mixing in the Process Industries, edited by Hanby, Nenow, and Edwards. This is the mass transfer coefficient, and this is the stirrer speed. So when the particles are on the base of the vessel, part of the mass transfer occurs by diffusion through the bed of settled solids. As the speed increases, we reach the just suspended speed. And there's a slight increase in the mass transfer coefficient where we have this power per unit mass to the quarter. And eventually we reach a region where the mass transfer coefficient levels off when surface aeration starts to occur. So if we double the speed, we get 8 times the power input because the power is proportional to the speed cubed. And the 8 to the power 1/4 is 1.7. So 8 times the power doesn't even double my mass transfer coefficient. So again, we need to go back and look at the process
Richard,
result.
I'm sorry, perhaps something with the nomenclature, but diffusion mass transfer, it includes the convective mass transfer? It's not diffusion as we understand diffusion.
No, there's a film around the particle, right?
Ah, okay. So it's the let's say it's the thickness of the film that is reduced by increasing the Reynolds of the speed. It reflects. Okay,
exactly right. Exactly. Yeah. So we're looking the KL, the mass transfer coefficient that we're looking at, is based on the diffusion through the film around the particle. And I'll actually say a bit more about this in a minute. But yes, okay. So we're not looking at the liquid phase mixing. We're assuming the liquid phase is well mixed, and the rate limiting time step is diffusion through the film around the particle. Exactly. So other things may be going on. Is there heat transfer? Is there liquid phase mixing? Is there gas dispersion and others? So although we can, this is, if we're only looking at solid suspension, this is what we're designed for. But we need to look at the other things that may be going on in the process as well, and make sure that we're not neglecting them in terms of our sizing. So when we're looking at the ores, we crush the ore and we extract a valuable, usually a metal, from inside the particle. So the Sherwood number estimates the mass transfer coefficient between the liquid and the surface particle. The diffusion through the liquid film at the surface of each particle is limiting. But sometimes the mass transfer and reaction occurs with a component inside the particle, in the pores. So it could be a catalysis if we're doing a hydrogenation, and it could be an extraction. So we need to take that internal diffusion into account. And the classic way that this is covered in chemical engineering, reaction engineering, is to look at the Taylor modulus. So when the value is high, we're reaction rate limited. And it says that throughout the pores, the rate of reaction is limiting, diffusion is fast. But generally, we're going to be internal diffusion limited. We're going to be at a lower value. And if we look at the concentration of A in the liquid phase at the surface divided by the concentration at the surface, if we have a small value of phi, the concentration at the surface or inside the particle is very close to the surface value. But if it's small, it can go to zero. So the rate of mass transfer that we can affect through mixing is the diffusion through the film, and this is back to your comment. So the concentration at the surface is smaller than the concentration in the bulk. We have a concentration gradient through the film. But this is the only thing that we can affect through mixing. The only to increase the rate of the process once we're operating at the optimum just suspended speed is to make the particles smaller, to reduce the distance over which the internal diffusion has to occur. Okay, are we all good with this before I move on? Okay, good. So what if we need particle distribution? So at NJS, no particle is stationary for more than 1 to 2 seconds, and it's the optimum for mass transfer. But sometimes we need more uniform distribution. If the slurry outlets at the top of the vessel, and certainly in crystallizers, we want to have a more uniform solids distribution, so the growth rate onto the particles is homogeneous throughout the batch. So there are less reliable correlations for agitator design, but we have to do it, and it does result in a significant power increase. So this is some charts taken from a paper written by a guy called Kees Burman, who worked for Shell in the Netherlands. And he had access to a tank that was 4.3 meters diameter in the plant. And he had some lab units. So this is a chart taken from a vessel in which was 0.5 of a meter diameter. So what we're looking at here is the normalized height in the vessel. This is the liquid surface, and this is the concentration normalized by the average concentration in the vessel. So at low speeds, we've got more particles in the bottom portion of the tank, and at the surface, no particles. We increase the speed to 290. Some of the particles in the base of the tank are picked up towards the top of the tank, and we increase the speed further, and we get almost uniform minimum variation, uniformity of the solids. So we've doubled the speed to get from this condition where we're operating. So NC on this chart is the just suspended speed. We go from 0.9 of the just suspended speed to 1.9 times the just suspended speed. We double the speed, we increase the power by a factor of 8. So you can have it if you want it, if you need it, but it's going to cost you. So this is a result for a single impeller. What do we do in practice? So this is the single impeller operating at the just suspended speed. It's a wide blade hydrofoil operating at 377 RPM. So this, I'm going to stop this I'm going to start this one. So look at the speed. This is the same single impeller, and we're going to increase the speed. The cloud height goes up, and we get to 90% uniformity at about 610 RPM. So that we can do this if we need to with a single impeller. But what we do in practice is to put a second impeller on the shaft. So we've doubled the power input, but we still get our 90% uniformity. So what's happening is we've got this cloud lifted up about halfway, and then the second impeller picks up the particles at the top of the cloud and lifts them up to the top of the tank. So if you need uniformity in your process for whatever reason, the way we're going to approach this is to design the lower agitator to operate at the just suspended speed, and then put a second impeller above it on the shaft. And if it's a taller tank, maybe even a third impeller. The final thing I want to talk about with solid suspension is erosion. This is a really difficult problem to deal with, especially in minerals processing. So there are two types of erosion. The first is sliding, where the particle slides along the edge of the blade, and the second is impact. And the region where erosion occurs is at the tip of the blades. The particles get caught up in the trailing vortices. They get accelerated, they have hit the blade tip at a high velocity, and the blade erodes very quickly. So the erosion rate is a function of tip speed, the concentration, and how hard the particles are. So the higher the concentration, the higher the frequency of collisions. So this is a picture of a 4-bladed Rushton turbine that was being taken out of a plant, and you can see the holes eroded through the blade. And this is the same, from our lab, a 4-bladed Rushton turbine that's been coated with layers of paint. And you can see where the regions where the paint has been eroded away match up very well with the regions where the erosion has occurred in the plant. So what do we do? The erosion rate is determined by the local energy dissipation rate in the trailing vortex, which is a function of the tip speed cubed and the projected height of the blade. So the correlation for the just suspended speeds shows that a small diameter impeller is most efficient for suspension, high tip speed, high energy dissipation rate. So if we know we're dealing with a slurry, where blade erosion is possible, the recommendations that we follow are to keep the tip speed below 5 to 6 meters per second, increase the impeller to tank diameter ratio, increase the impeller power number, so we'd use a wide blade hydrofoil or a pitch blade turbine rather than a narrow blade hydrofoil, and also increase the number of blades. So we put more power in, lower the tip speed by adding, so rather than a 3-blade, we might go to a 4-blade impeller. This is another CFD. This is the trailing vortex coming off a pitch blade turbine, and you can see the vortex rolling up at the tip of the blade. So all impellers suffer from this effect if they're not designed properly. So processes with solids have presented major issues for plant startup and operation in the past, and I would say continue to do so. We need a good definition of the process result. What does the operator of the plant need, suspension or distribution? We need accurate basic data, particle and liquid densities, which are pretty easy to get, viscosity of the fluid, particle size and distribution, which is generally harder to get, and the concentration. The just suspended speed can be reliably estimated, and it's the optimum condition for solid liquid mass transfer. And the design rules for uniform distribution are not as reliable, but I've shown you how we would approach it. Design for the just suspended speed with a single impeller, and then add a second impeller on the shaft. So let me stop there and ask if you have any questions before we move on to gas liquid mixing.
Okay, any particular question? Perhaps some comments, Richard, regarding when you have either particle sizes or distribution or bubble or droplets. There is a not concern, but we still are using a number that's, let's say, pack all the information in a single number, being one of them a solder diameter, which to some extent explains when you have, I mean, funny distributions. However, still we're using a number. There is an approach that uses, for example, a distribution. I mean, for example, in chemical reactors, you use a K, but you also can use, when you have different things, you can use distribution for this value of K, like a Klimper model, for example, when you impose a distribution. There is models that uses distribution. This is one of the questions from Felipe Contreras and Felipe, well, guys from industry.
Yeah, so those distribution, the D43, the D32, they represent the distribution with a single number, and the D32 has a very specific meaning, which we're going to talk about next. But you could, if you know your distribution and you know the mass, you segregate by particle size, and you know the mass of particles in each bucket, you could do these calculations for each class of solids. So, and that would be a more accurate way of assessing. I mean, for example, if we're dissolving, the fines will dissolve very quickly. The larger particles will dissolve more slowly. So I guess it depends, you know, what aspects of the process are you interested in? Is a generic single value going to give you all the information you need to design the equipment, or do you need to take a closer look at all the classes of size of particles within the distribution? So yeah, I completely understand the question, and I think the answer is it depends on what you're doing and trying to do in the process. Does that make sense?
Yes. Okay. Thank you.
Okay.
Can I ask you?
Yeah, sure.
I mean, I work in flotation, okay?
Right.
It's very important for me to keep the suspension of the particles in a flotation cell, and at the same time, you use the impeller to disperse the air. So essentially, there are two objectives there. One is to get smaller bubbles, and at the same time, you want to keep the particles in suspension, you know? Right. And apparently you have two things that you worry. One is complete of perfect dissolution or distribution. Actually, you essentially go against distribution, and it's not the same. You are not considering, for example, these two objectives that we have in flotation.
Yeah, but if you bear with me, I'm about to talk about that.
Okay.
Three-phase mixing, right?
Yeah, three phases.
A gas, a solid, and a liquid. So yeah, I completely understand your question, and I'm going to address three-phase mixing, and in a generic way, not necessarily specifically addressed at flotation. But no, I completely understand you need your particle suspended, you need your gas dispersed, you need good contact between the particles and the bubbles so that they can adhere, attach, and then be lifted up to the froth at the top of the vessel. So yeah, there's a number of things going on that we need when we think about our process result. What are all the things that we need to achieve? Gas dispersion, solid suspension, particles attaching to bubbles, bubbles rising to the surface without having the particles broken off. So yeah, it's there are many things going on in the tank that have to be optimized for the process to work effectively.
I'm a little bit hesitant to ask you things, because I don't want to take you out of your subject, I don't want.
Oh no. It's perfect. I just want to say it's perfect. I mean, I am talking in a very general way about mixing, and so what we ultimately want to do is to apply that general knowledge to specific processes like froth flotation. So when you ask me questions, I'm learning. And hopefully, seriously, I'm learning from you as you ask me questions, because it makes me think about, well, how do I apply the general mixing rules to a specific mixing application like froth flotation? So no, I enjoy the questions.
Okay, then I'm going to take advantage of that. In flotation there is an impeller, but there is also a stator, and you are not discussing that, or maybe you will. Well,
I can tell you no, I won't. But the stator, yes. If you think about inline high shear mixers, they have rotor stator. It's a rotor stator. So forcing the fluid through the stator breaks up, increases the stresses, makes the bubbles smaller.
Okay.
So no, it's a very specific application. But in the interests of time, I'm looking at my watch. Let me talk about gas liquid mixing. And like I said, I can hang around all afternoon to talk about mixing if anyone wants to talk about specific things. Okay. So we've talked about solids dispersed. Now we're talking about gas bubbles dispersed. Again, we're generating area for mass transfer between the phases. And an example might be to strip a volatile compound from a liquid product. If we're doing an aerobic fermentation, we're stripping out carbon dioxide. There may be a chemical reaction. And again, we need to determine, are we mass transfer limited? What can we do to increase the mass transfer rate if we are mass transfer limited? And is there a third phase? Froth flotation, it's on my list. Froth flotation. Do we have a solid catalyst for hydrogenation? Do we have a solid reactant? If we're purifying lithium carbonate, we bubble carbon dioxide in to make soluble bicarbonate, do solvent ion exchange, and then we heat that solution to bubble off the carbon dioxide and produce a pure lithium carbonate crystal. So as a molecule of gas transferring from the gas bubble to the liquid, or vice versa, the rate of mass transfer is dependent on the solubility of the gas in the liquid. Carbon dioxide is more soluble than hydrogen. The effective temperature and pressure. High pressure is good, higher temperature reduces the solubility. And the diffusivity of the gas in the liquid. How easily does it move? So hydrogen, which is a small molecule, diffuses faster than carbon dioxide, all concentration gradients being equal. And how viscous is the liquid? So I don't want to spend too much time on this in the interests of time. I mean, you've seen this before. Just a couple of points to make. We assume that the gas phase is well mixed, that the concentration in the film on the bubble side is uniform. In the liquid, the concentration is gradients are going to depend on the rate of reaction. So if the concentration, if the reaction is fast, the concentration of A in the liquid is going to be lower than the equilibrium concentration. If the reaction is slow, the concentration in the liquid phase is going to be close to the equilibrium concentration. You have to have a gradient for molecule A to move into the liquid. And similarly, if the reaction is slow, the concentration in the film will be equal to the bulk concentration of B. But if it's faster, some B will be consumed within the film. And that's when we have enhancement of the mass transfer due to the consumption by reaction. So we can write our equation, rate of mass transfer, KLAV, times the concentration gradient, is minus the rate of consumption, is equal to the rate of accumulation. So if the reaction is fast, we need fast mass transfer rate to keep up with the consumption, or vice versa. And often, so ideally, the concentration in the liquid phase could go to 0, maximum driving force. But in some processes, you have to maintain a certain concentration of the transferring molecule in the liquid. And the classic example is hydrogenation to prevent catalyst deactivation. And the second is aerobic fermentation, where we have to maintain a certain oxygen concentration to prevent the bugs from dying. So if rate of transfer is equal to rate of consumption, the differential term goes to 0. And that's essentially an ideal place to be operating. So if the reaction is slow, we can get enough mixing simply by bubbling the gas through the liquid. The mixing energy comes from the rising bubbles. Large volume, long residence time, low mass transfer rate. If we have a fast reaction, we only need a small volume, short residence time, but we need a high energy dissipation rate and a high mass transfer rate. And essentially all the reaction occurs in the film around the bubble. The molecule A never makes it into the liquid. So we can use an inline static mixer. And in between the two, we have a stirred tank, which has a large volume. We get mixing from the energy of the rising bubbles and the impeller. So the equipment selection should be made by comparing rates of reaction and mass transfer, but these are often not known and can be difficult to measure. If I'm doing, say, something with fluorochemicals. So the agitated vessel is commonly used as a compromise, has a high holdup and high interfacial area, and also it's good for suspending particles if they're present. And the design rules are very similar to solid liquid mixing, where bubble buoyancy causes the bubbles to rise and leave the system. But in solid liquid mixing, the particle size is fixed by what we feed to the vessel. In gas liquid mixing, the bubble size is determined by the intensity of agitation. So just like solid suspension, there's a minimum speed for dispersion and a maximum speed required to recirculate the bubbles to get uniform distribution of the bubbles throughout the system. Once we've calculated the agitator speed, we can calculate the power required to drive the agitator. Then we want to look at the holdup of the dispersion occupied by the bubbles and the mass transfer coefficient, which is ultimately what we're after to get our process to work. So the impeller type that we're going to choose is dependent on the gas flow rate. At low gas flow rates, we'll use a wide blade hydrofoil. At high gas flow rates, we're going to use a radial turbine, which pumps the gas bubbles out towards the wall. Traditionally, we use a Rushton turbine. New developments are a concave blade, commonly called a Smith turbine, and parabolic turbine. So we need a high local energy dissipation rate to create small bubbles. And if we create small bubbles, we have a high interfacial area for mass transfer. So if we have a second impeller, if the tank is tall, we're going to use an axial flow impeller to promote the liquid phase mixing. And in some cases, we might want to create a vortex to draw unreacted gas down from the headspace of the reactor. So here are the impellers. This is the medium solidity hydrofoil with a power number of, sorry, I didn't mean to start that, 0.7. Then we have the Rushton turbine, which was developed in the 50s for gas dispersion. Then the Smith, which is the 1980s, 1990s version with a blade that's made of pipe, half pipe. And then we have an impeller with a parabolic blade. And I'll explain this evolution of flat to parabolic blades as we move through the talk. Let me just turn the sound off here. So this is we're going to talk about the transition from flooded to loaded. So when the agitator's running at low speed, the buoyancy just allows the bubbles to pass through the impeller and rise up to the liquid surface. And as we increase the impeller speed, the inertia in the fluid flow can take hold of the bubbles, overcome the buoyancy, ultimately drive the bubbles out towards the wall of the tank, and then recirculate the bubbles underneath the impeller. Let's start this one. So what we're going to do here is we're just going to run the impeller at a certain speed, and then we're going to turn the gas on. So let me just move this forward to when the gas bubbles appear. Oop, too far. Here we go. So here comes the gas. And you can see how the surface rises up above that line, where the tank's actually in a square tank so we can get a better picture of what's going on. But the difference in heights is the holdup. That difference in height is proportional to the volume of bubbles held up in the liquid. So when the agitator's running at low speed, it's behaving like a bubble column. Bubbles just rise up to the surface. As we turn the agitator on, the inertia can take hold of the bubbles and drive them out to the wall of the tank. And that's called the flooded condition. That's the minimum speed at which we would want to operate. And as we increase the speed further, we can get gas bubbles recirculating underneath the impeller. And the other way to look at it is constant speed and reducing the gas flow rate. At constant impeller speed. Constant speed, increasing the flow rate drives us into the flooded condition. So I haven't got the correlations in the talk, just in the interest of time, but we can predict the flooded and complete dispersion speed for different types of impellers. Now, when we turn the impeller on, for some impellers, the power drops. So what we're looking at on this y-axis is the gas to ungassed power for the impellers. So the flat blade is the Rushton turbine, and these researchers looked at different shapes of blades. This is the Smith turbine if it's moving in the right to left direction. They looked at angled blades, and then they have parabolic blades. So what happens is as we turn the gas on, the power drops for some impellers. And we'll talk about why that happens in a second. We've got a high pressure zone on the front of the blade and a low pressure zone on the back of the blade. And the bubbles want to collect in the low pressure zone. So as the flow hits the front of the blade, the gas cavity that forms on the back of the blade smooths the path that the liquid has to take to flow over the blade, and it reduces the drag. And if the drag reduces, the power required to drive the impeller through the liquid goes down. So the idea behind the half pipe, the concave blade and the parabolic blades is to fill this space where the cavity wants to form with metal. So as the gas is turned on, the reduction in power is smaller than it would be for the Rushton turbine. So this chart is a blow up of one of the ones we just saw. So the Rushton is the open square circles, and we see a power drop of about 40% from 1 to gas ratio from 1 to 0.6. The concave is the dark circle. So the dark circles are the Smith turbine, and the down pointing triangles are the parabolic blades. So we're going to see that the holdup and the mass transfer coefficient are functions of the gas to power input by the impeller. So if we can find an impeller that isn't affected by the presence of the gas, it makes the operation of the process much more effective. if you are using a Smith turbine or a Rushton turbine, this is the equation we use to calculate the power reduction, PG over PU. And this is data that we've taken in our lab. This is the red circles are our parabolic impeller. The blue circles are the Rushton turbine, and then the orange is the fit of the Bakker, Myers, and Smith correlation. So it works very well. But generally, if we would use, if we can, a concave blade impeller to minimize the loss of power.
Sorry, one question. All experience consider buffless or the
Yeah, okay, so good question. Very good. So everything I've talked about today so far is for baffled tanks. They all have baffles in, whether for solid suspension or for gas dispersion. Yes, good point. Okay.
Thanks.
Okay, so the first thing we're going to be concerned about is the gas holdup, and it's the ratio of the gas volume to the total volume of dispersion. So it's affected by the bubble size. Smaller bubbles have a slower rise velocity and will stay in the liquid for longer. The distribution of and circulations of the bubbles throughout the liquid, and the growth due to coalescence of the bubbles as they circulate. So once they get away from the high shear zone, if they bump into other bubbles and the interfacial tension is high, the bubbles will coalesce. Now, generally in the real world of the chemical industry, there's usually something dissolved in the liquid which will stabilize the bubbles. But it's something that needs to be taken into, be at least thought about. What's the tendency of the bubbles to coalesce once they move into the less agitated regions of the tank. And then the other thing we're interested in is the interfacial tension. So how much energy is required to break up the bubbles, and how likely are the bubbles to coalesce if they collide? So holdup is important because the interfacial area per unit volume is 6 times the holdup divided by the D32, the Sauter mean diameter. So the higher the holdup and the smaller the bubbles, the higher the interfacial area for mass transfer I have. So lots of work has been done on this. And so I'm citing a paper from a PhD thesis from 1983. Everybody who does work in this area ends up with a relationship that looks like this, with the gas to power input per unit mass by the impeller and the superficial gas velocity. So this guy, Colin Chapman, correlated holdup data for 2 sizes of Rushton turbine, 2 sizes of pitch blade turbines pumping up and pumping down in air and water. So as long as I know the power input by the impeller under gas conditions, I can make an estimate of the holdup. But the point also to make here is it's air and water. It's not there's nothing in this. Is a coalescing system. So if we look at the mass transfer coefficient, we look at the KLA, the KL times the interfacial area per unit volume. KLA is a lumped parameter, and A is a function of the D32. So we can infer if KLA is going up, KL is weakly dependent on the mixing to the power input per unit mass to the 1/4. If the power per unit mass goes up and we see an increase in KLA, it's because A is increasing. We're making smaller bubbles. We get increasing our interfacial area in that way. So KL is the liquid side mass transfer coefficient, and we're looking at renewal of the liquid within the film surrounding the bubble as a process by which KL increases. A is the interfacial area per unit volume, and we're making smaller bubbles. The bubble size is dependent on the mixing intensity or shear that the gas experiences as it passes through the blades of the lower impeller. But generally, it's difficult to measure. This is why people doing research in gas liquid mixing present their results as KLA. So again, lots of researchers have done this. I'm citing research that was done, published in 1979. And everyone who's done work in this field since that time get the same kind of results. So again, we're looking at the gas to power input per unit mass, superficial gas velocity. But what Van Riet found was that you get different constants if you have water, which is a coalescing system, or you have a strong ionic solution, which is non-coalescing. The constants change. They are system specific. So lots of academic research is done in air and water. Sometimes they add a surfactant. You have to be careful because the correlation is dimensional. And the value of A depends on the system of units used. So Van Riet used watts per cubic meter for the power per unit volume and meters per second for the superficial gas velocity. But if you express the power per unit mass as watts per kilogram, density of the liquid is taken into account. So the constant becomes 0.412. So it's 0.016 times 1,000 to the 0.4. So you have these correlations are dimensional. Correlations in the literature are very academic. Air and water, these constants change in real systems. So let me say a few words now about three-phase mixing. Design rules exist for two-phase mixing. How can they be modified for three-phase systems? So a number of studies have been done over the years looking at this, and they generally all come up with the same recommendation for scale-up. So Chapman was sponsored by ICI. Back in the 80s, looking at the oxidation of paraxylene to terephthalic acid. Nafis Ahmed works at the University of Newcastle in Australia, and his work was sponsored by the minerals processing industry. Guy called Lane and then Ninow have looked at general three-phase mixing in the 1990s and the 2000s. So Ahmed proposed that you scale up at constant torque per unit volume. So what does this mean? You find the torque per unit volume that you need to suspend the solids. Then as you turn the gas on, if the power drops and the torque drops as a result, you have to increase the speed to maintain constant torque. And so this is the rule. And we've done tests recently ourselves to look at this. This is how we would approach the design of a three-phase system, just generally. Three-phase system, not talking about froth flotation here. Determine the torque required to just suspend the particles. Then look at the effect of the gas. And if the gas flow rate is low, then your design is finished. If the gas flow rate is high, you may have to increase the speed above the just suspended speed in the ungassed liquid to make the process work. There aren't any solids in these pictures, but one of the things we've been looking at is the way the gas is sparged into minerals processing tanks. We're looking at these caps that fit over the gas sparging pipe to keep the solids out of the gas feed pipe. So this is a flat plate. And this is a cone. So the gas is coming in inside the cone, coming out, being dispersed. But if the agitator turns off and the solids settle, we won't block the gas pipe. They'll be kept out by the cap. So gas liquid mixing, we need, again, good definition of process result, basic data, gas flow rate, temperature, pressure. Are there solids present? If there are, they have to be suspended for mass transfer. We're going to design for flooding as a minimum, but more often complete dispersion. If we know nothing about the reaction, we are going to design for the complete dispersion speed. You've got to take care with the correlations for holdup and mass transfer coefficient. They're dimensional, and the constants are system specific. The constants that we read in the literature show us the cause and effect, but they don't. It's very dangerous to use them specifically for design. Three-phase system design we determine the ungassed torque per unit volume and scale up, maintaining a constant value. And the final thing, I've been asked about this before, and I need to say a few words. Some people look at disparaging the gas down the shaft and having it dispersed at the lower impeller. And we need to assess the costs. That's a much more complicated system. You're still pumping the gas into the vessel, and we need to think about the costs and benefits of actually doing that. So I think this is my final chart. I have some backup charts if you're interested to see them. But if you have any questions, let me. I'll stop here and hopefully be able to answer them.
Okay, Paula, please join us.
Yes, I'll do the question section now. Thank you, Richard, for a wonderful presentation. It was very interesting. It was packed with a lot of industrial data, but also with a lot of fundamentals. So I think it was a very good balance. A lot of information, but that's very good because it also allows us to see, and also allows our students and our new engineers to see what is going on in the world of mixing today. So, well, we have some, we don't have too many questions in the chat, just a very interesting discussion took place. And on questions, let me see what's in the chat first. Here's one question on how many impellers does Philadelphia Mixing Solutions have in their catalog? That's an interesting question. An estimate, maybe?
I've actually got in my office, I've actually got a table with data. Bear with me a sec.
Okay, thank you.
I have a table pinned to the notice board in my office, and it's 56.
56. Okay.
Yes. So, and the point I'd make is there's a lot of impellers, but you have to choose the right one for your process.
Exactly.
Okay.
Thank you. Does anyone have any? If anyone has any questions, you can please raise your hand, or you can write them down in the chat if you want to. Any questions?
Okay, let's continue, I think.
Okay, I think I have a question though. Well, we were what I was saying about, you know, the balance between industrial data, you know, and industrial experience, along with the fundamentals, the mass transfer fundamentals. I think it's vital for especially for engineering students. But in that respect, I'd like to know what do you think are the, if you would have to choose 5 topics, you know, that would have to be covered in a mass transfer course, what do you think those topics will be on mixing?
On 5 topics in a mixing course, well, the first thing I think is the fundamentals of impeller characteristics, and how do we quantify the flow, the shear, the power, the efficiency. The second thing would be just simple liquid phase blending. If say doing pH control, and I've got a waste stream and I'm adding an acid or a base, how long do I need to mix to ensure that the contents of the vessel are well mixed? Next would be the same, but for viscous and non-Newtonian fluids. So I mentioned earlier that there's interest in high concentration slurries, which are viscous and non-Newtonian. They behave as single phase systems. So how do we apply the rules to those systems? The fourth thing would be mixing and chemical reactions. So if you have like A plus B makes C, but if I'm doing a reaction where A plus B makes C, but C can react with B to make a molecule that I don't want, in a perfectly mixed environment, the outcome of that reaction is governed by kinetics, the ratio of the rate constants of the 2 reactions. But that assumes that I'm mixing fast enough for the reaction to be taking place in a well-mixed environment. So how do I determine that? And this is really important. You know, if I overreact, I make a byproduct. I waste raw materials and I have cleanup costs. So I would talk about that. And then let's see, 1, 2,
3,
1,
4.
2, 3,
One
4.
more.
Oh, well then, okay, so give me 6. Then I would
Okay.
talk about solid liquid and gas liquid in more detail as separate topics.
Right.
And
You can add more if you want.
well, I'm just trying to think about. So okay, so number 7 then might be, and I'm not sure how important this is. We don't see this as often, but if you are making a liquid-liquid dispersion, emulsions, liquid-liquid dispersions, solvent extraction type processes, how do I size an agitator for liquid-liquid dispersion? So in some cases, I want to make a dispersion that's stable, is an emulsion. My product is the dispersion. And in other cases, if I'm doing, say, solvent extraction or a chemical reaction, I want the mass transfer to occur, but don't want the bubbles to be so small that they won't separate afterwards. I have to control the drop size. Another topic, I mean, which again, I'm not sure how interested folks on the call here is mixing with motionless mixers, static mixers, inline, like, and also jet mixers, mixing with the jet rather than an impeller. That could be another topic of interest. And then mechanical, you know, chemical engineers are focused on the process. Mechanical engineers are focused on the machines. We're selling machines. The operators are using machines. So it's good for the chemical engineers to have some appreciation of what concerns the mechanical engineers, like critical speed, the natural frequency of the shaft, the torque, the bending moment, the gearbox sizing, materials of construction, the things that chemical engineers don't focus on. We actually have to have a good discussion with our mechanical engineering colleagues to make sure that we build a mixer that will do the process, the mixing part, but also will run for 10 years, for 15 years. I change the oil, I check the bearings, check the oil seals. It runs smoothly for 10 years, because every time that mixer shuts down unexpectedly, we're losing money. We have to fix it and we lose production. So the mechanical aspects are important and need to be understood by chemical engineers. How many is that? You're on mute, Paula.
Sorry. No, that was 9 topics, but it's still good. I think it would make up a really good course.
Well,
thank you, Richard.
if you're interested in putting a course together, I have lots of material. I teach at Delaware and Rowan University, and I would be more than happy to share that material with you. The more people who get taught about mixing in the world, the better off we'll all be.
Yeah, I agree with that. Thank you, Richard. Do you have any more questions?
I would like to offer a comment.
Sure, absolutely.
Well, I appreciate your seminar. I clarify a lot of wrong ideas I had, you know, mainly because actually I'm not in the field, as I mentioned to you before. I am working in flotation, and mass transfer is not a big issue in the column or in the cell, and that's what I think I miss, you know. Well, in your case, right? You have if you have solids and droplets or solids and bubbles, essentially your view is how mass is transferred between either the gas to the particle or thing. But And as you say, mixing is not very important there, because you don't change much the mass transfer coefficient, by just mixing, However, in flotation, we still have the problem that we need to make contact between the bubbles and the particles. And I believe what is happening, close to where the gas is dispersed, where you have much intense turbulence, is completely different from what is happening close to the walls. So essentially the whole volume, we may have very good distribution of bubbles and particles, but it's very important also the turbulence or the conditions for colliding,
Sure.
and that is not uniform, in spite you having very nice uniform distribution of the particles and the bubbles. So, well, that's my problem essentially, but I appreciate, your seminar, and I will examine your presentation much more carefully. Even I may try to connect with you in the future, but essentially I want just to leave you this comment, that I believe I still need to get a little bit further on all the ideas that you put in my mind.
Yeah, the way I picture this, and in flocculation processes as well, where it's just particles colliding, you need to create surface area. You need a region of sufficient shear to break down the bubbles, and as those bubbles move away, you need to be in a region that's mixed well enough that the particles are suspended and are brought into contact with the bubbles at a velocity where they can collide and stick. If they're too fast, they might bounce off. If they're too slow, they may not stick together. Right. And so it's a balance. It's a balance between too much shear, which ultimately could strip the particles off the bubbles, and not enough shear where, or say not enough mixing where the particles aren't suspended well enough. They aren't brought into contact with the gas bubbles well enough. So yeah, there's a trade-off, and I always like this idea of the rate limiting step, which is driving our process. Is it the making of the bubbles? Is it the collisions? Is it, we ultimately, I suppose, you want the gas not to come back to the impeller. Yeah. You want it to be broken up, meet a particle and carry it up to the surface and never come back to the impeller. So there's that trade-off. There's a trade-off there, and I think get back to this side, the process result. What are we trying to achieve? What are the physical processes that govern the achievement of that process result? And having that conversation and writing it all down and coming out with an understanding. How does mixing affect the performance of the process and achievement of the process result? But I starting at kind of that high level, and then delving down into, well, what's going on and how does mixing affect it? That's what I always like to try and do with anyone, whether it's someone with an existing process or a new process. Understand how the mixing affects their process. That's my goal always.
Yeah. Well, again, I appreciate your presentation, and thank you very much.
No, you're very welcome. And let me say just one thing. There's a couple of edits that I know I need to make to the charts, which I'll make this afternoon, and then I'll send the updated version to Claudio to distribute to everyone on the distribution list. I'll also send the article, which was in Chemical Engineering magazine, about the flow and the shear, the characterization of impellers. What else did we talk about? Oh yeah, the model, the solid suspension model. I'll send you that paper as well. If you're not interested in them, obviously you can hit the delete button, but we covered a lot of material, and I'll just be able to give you a bit more background from where we came from as to get to those conclusions. And I'll also send you my email address. Oh, there it is. There's my. If anyone wants to talk to me, or whether by email or by phone or by Zoom or Teams, be more than happy to chat with you about mixing problems. Any other problems, you're on your own, but mixing, I'd be happy to spend time with you to chat.
Thank you very much, Richard. I think we have one more question from Francisco Sandoval, and with that would be our last question because it's past 2 o'clock. Okay, the question is, it's here on the chat, is there any impeller that is more used than others in the company that you are working? Does the impeller cost affect the selection of choosing the correct one for the process, or does it depend on the type of solution that you are mixing?
I think those two things are related. So if we look at the process, we start from the process, that there's going to be a type of impeller that we immediately will think is the right one to use for the process. And then we learn more about it and determine whether or not it's the right one to use. But the one that we sell the most of, I would say, is the wide blade hydrofoil. So if you go back to the chart, can I share my screen again? I'm sorry.
Yes, of course.
Let me go back to this one. Share, and I'm going to shoot way back to the start. So we had the pictures with the impellers, and we're saying what's high shear, what's low shear, and nearly there. Here we go. Okay, so the one that we sell, I would think we sell most of, is this one, which is a wide blade hydrofoil. We sell these as well. The one on the right is one that we use in wastewater treatment. It's a special design for use in wastewater treatment. For gas dispersion, we would use either the Smith turbine with the half blades, or the GDX, what we call the GDX with the parabolic blades. We don't sell so many pitch blade turbines these days. Tend to go more towards these hydrofoils. And then we have other impellers that we use for viscous mixing, which are a different class of impellers altogether. And hopefully, if we can arrange another date, convenient time in the future, I'd love to talk to you more about mixing of viscous liquids, mixing of viscous slurries. I think that would be an interesting talk for us to have. So, short answer to your question, it's this one, this wide blade hydrofoil. That's the one that we seem to sell most of these days.
Great. Thank you, Richard. And Francisco says, thank you very much through the chat as well.
Okay, yeah, thanks everybody. I thanks for spending hanging on and spending the time. I realize we've overrun slightly here.
No, but it's been very, very interesting, and I think we'll be all looking forward to the material that you will send, Richard.
Oh,
so
yeah, absolutely.
Thank you very much.
No, thank you, everybody.
Okay, so I'm finishing this recording. It will be sent in about 15 minutes to all the people.